So remember, for any reaction that's reversible that can reach equilibrium, we can write what's called an equilibrium constant expression. Capital K equals, your products over your reactants raised to the power that is the coefficient, Kc meaning concentrations, or you could do Kp indicating partial pressures instead. If you need help looking at how to do that, see one of my past videos. So if you are given equilibrium concentrations, you can plug those in and you can calculate what K is. And if you were to do that for this reaction, you could actually look up K values for a lot of different reactions at 472 degrees Celsius, because at a different temperature it would be different. K depends on the temperature. Let's say for this reaction, you get 0.105 as your K value. Now, let's say I am creating a mixture, and in my 1 liter container, I put in 2 moles of H2, 1 mole of N2, and 2 moles of NH3. How do I know if I'm at equilibrium to start with? So remember in the past, you could see my past videos. If you have initial data, you can always create an ice box, figure out what your equilibrium concentration should be with that. But rather than going through all that work, there's a way that at any point in time, if you have concentration data, usually initial, but it could be any point in time, you can actually figure out if you're at equilibrium by plugging into this expression. If I plug in my concentrations for NH3, N2, and H2, and I'm at equilibrium, I should get this value at this temperature. So you can always check whether or not you're at equilibrium at any point in time. Okay, so if we plug in initial data, just remember that it's not at equilibrium necessarily anymore, so we're not going to call it the equilibrium constant anymore that we're calculating by plugging in initial stuff. So it's still a fraction, it's still dividing things, so we're going to call it a quotient Q. So Q is really just plugging in your initial data into your equilibrium constant expression. That's it. It doesn't have to be initial data. It could be at any point in time. It's a check to see whether or not you're at equilibrium. So let's do that. Let's plug in right now and figure out, let's plug in, this data. Let's make sure we're in molarity. It's a 1 liter container, so your moles just become molarities. And remember, once you calculate K or Q, it's going to be a unitless number. I get 0.5. So my question is, at this temperature, am I at equilibrium? No, I'm not at equilibrium to start with, because 0.5 is not the same as 0.105. So if my Q does not equal K, I'm not at equilibrium. Now, if I'm not at equilibrium, that means the forward and reverse reactions are not occurring at the same rate, and the reaction is either going forward, the forward rate's faster, or I'm going in reverse, the reverse rate's faster. So how can we figure out if I'm not at equilibrium, am I going forward or reverse? We can compare this number to K. So if I think about it, okay, 0.5, is this higher or lower than K? It's higher. It's too high. I need to bring this number down. So how can I bring this number down? This means that my numerator's too high. I need my numerator to get smaller. What's in my numerator? Product. I need product to get smaller. And I need my reactant to get bigger. What's in my my denominator, my reactant, to get bigger. So basically, I need to go in the reverse direction. Okay, so to reach equilibrium, this quotient has to decrease. So to decrease, how can I get it to decrease? Go in the reverse direction. Use up the NH3, the numerator will come down, create the N2H2, denominator will come up, and this number will eventually get to 0.105. So basically what this is saying is the reaction is going to proceed to the left until it reaches equilibrium. It's going to go in reverse, and then once it's at equilibrium, the rates can now be equal. Now, a lot of times a follow-up question after figuring out which way your reaction shifts is what happens to the pressure. If you remember, what phases are we looking at for pressure? For pressure, we're looking at gases. Why? Because if we think about our ideal gas law, PV-nRT, right, PV-nRT, for the same volume, for the same temperature, for the same R, which is a constant, if the moles goes up, if N goes up, then P goes up. So if you're shifting in a direction that creates more moles of gas, the pressure is going to go up. And if you're shifting in a direction that creates less moles of gas, your pressure is going to go down. So let's see, in this scenario, we said we're shifting left. So we're going from 2 moles of gas, consider your coefficient, to creating 3 plus 1, 4 moles of gas. So the total pressure would go up because our moles of gas have gone up. Now it won't entirely double because this isn't going to reach completion. I'm not going to completely use up my 2 moles of these 2 gases to create 4 gases. I will at equilibrium have some product and reactant, so it won't completely double. If I look at 2 to 4 gases, it won't completely double, but it will increase and be somewhat less than double by the time I get to equilibrium, depending on what my K is. Okay, so again, Q is just a fancy way of saying, hey, we're plugging in our initial data into our equilibrium expression, and since it's not equilibrium stuff anymore, we're just going to call it Q. Again, it doesn't have to be initial, it can be any point in time as a check, are you at equilibrium? And a lot of times we're used to seeing initial stuff, we're going to create an icebox, but this is another thing you could do with initial data, so just be aware of that. A lot of people forget about Q. And you might see QC for concentrations, then you plug in concentrations. You might see QP, P for pressure, then you plug in partial pressures for your gases. Okay, so just to sum this up, if Q equals K, you're at equilibrium. Cool. Awesome. If Q is bigger than K, that must mean, okay, let's think of our expression. Numerator is product. So if Q is bigger than K, I've got too much product, too much numerator. So equilibrium is going to shift to the left to use up that product to create reactant, and it's going to go in reverse and keep going in reverse until we reach equilibrium when that Q comes back down to equal K. And if Q is less than K, that means, oh, wait a minute, my denominator is too big. What's in the denominator? Reactant. We got to bring the reactant down. We got to use it up. So we're going to go forward and create, which is to the right, and create product. And it'll continue to do that until we reach equilibrium, and then your rates will be equal again and your amounts will not be changing. But when we are shifting in a direction, your amounts are changing. Okay. There's a little shortcut if you want. Some people memorize this. If K is less than Q, it goes to the left. If Q is less than K, it goes to the right. But I just really like to think about it logically because it just makes sense. Again, the biggest thing about Q is people forget you can calculate it. So anytime you have initial data, don't forget you can, instead of doing an icebox, you can plug into Q if they're asking about which way your reaction shifts. Take a moment, try this example, and then we'll check our work. So in this example, they give me the temperature. The only reason for the temperature is that K depends on temperature. So if we change the temperature, K would change, but I really don't need it for the problem. Here's my reaction. And they give me all initial data. And a lot of times when I see initial data, I'm like, oh, let me do an icebox. But wait, let me first read the question. They're asking me about predicting the direction. And even A says calculate Q. Sometimes on the AP exam, they won't come right out and say you're calculating Q. They might literally just jump to which way the reaction is shifted, or are you at equilibrium. So don't forget, Q is an avenue, a way for you to do that. So I'm going to plug in my initial data. Since it's KP, I'm going to call this QP, and I'm using partial pressures. Make sure they're in atmospheres. You have to use atmospheres for partial pressures when you're calculating Q, even though Q is unitless. We're assuming we're using atmospheres. And when I calculate it, I get 16.4. Let's compare it to the K they give me in the problem. Notice I'm not at equilibrium because they're not the same. My Q is way too high, which means my numerator is too big, which means what's in my numerator, my products, which means I got to use those up. I got to go in reverse. The reaction is going to be shifted to the left. You're going in the reverse direction with this initial stuff in your container. The reverse reaction's happening until we reach equilibrium, and then the rates can start being equal. Okay, and then part C is what would happen to the total pressure. Let's look at our numbers of gases. And just as a reminder, if you have a solid or a liquid, we're not paying attention to that. We're looking just at gases. How many gases are on each side? I've got 3, I've got 2 moles on this side. I've got 3 moles of this side in the reaction. So if I'm shifted to the left, I'm going from 3 moles to creating 2 moles. I'm creating less moles, so therefore there'd be less pressure. Okay, and again, remember that I'm not completely going to completion where 3 moles is exactly turning into 2 moles, but I am going in a direction where I am going to be decreasing the moles over time. So just as a reminder, is what we just said, looking at PV, energy, and volume, R and T are constant. Anytime you're shifted in the direction to make more moles, more N, your pressure is going up. If you're shifting in the direction where you're making less moles, your pressure is going down. Again, you're not going to completion. You're still going to have some product and reactant, but you can use this as a way of figuring out, is it going to increase or decrease? And if you have the same number of moles of gas on each side, then your pressure is not going to change because you're not actually changing the number of moles of gas. So hopefully this helps you with Q. The biggest thing to remember about Q is that you can calculate it to figure out reaction shifts. So if they're giving you numbers, giving you data and asking you which way the reaction shifts or what's happening to the pressure or whatever, implying something about the reaction shifting, calculate Q.